Alright, so I'm recording this presentation. This is chapter 6 of the CCNA routing and switching course, and we'll be looking at the network layer, how the protocols work, how they're structured. We'll look at how routing works. Then we'll have a look at how routers are actually made. Basically, they're a computer, just a specialist computer. And then we'll finish off with looking at some basic configuration commands. So, network layer is the third layer of the OSI model, and it will talk to the layer at the corresponding recipient, as well as the layers above and below it directly. So it'll talk to the transport layer and the data link layer, as well as its respective copart at the other end. It is responsible for encapsulating the data that comes into the network layer. It is then called a packet after it has the addressing added, which is the IP address, and our intermediate devices will do routing based on this information, and at the final destination it is then responsible for the de-encapsulation of that packet. So we'll be looking at IP version 4 and version 6. We'll be not discussing any of the other protocols that run at this layer. So basically, the transport layer will send the data down, which will have the transport layer segment header as well as the original segment of data, and then the network layering will add the source and destination IP address header information, and this becomes known as an IP packet. So what are the characteristics of the IP protocol? It is a connectionless best effort and independent of all the media that it is transported across. So what does that mean? It is connectionless in that it doesn't need a response from the recipient before starting its communication path. It's like the mail. You just drop it into the letterbox and hope that it gets to the other end. Okay? So all that error detection and correction and that is done up in TCP. So here we have what I was just saying, that it's similar to post. You drop it, the data into the packet, it gets sent on its way and delivered to the other end, but you don't know whether it's delivered or not, and the recipient doesn't know whether it's on its way. So as those characteristics contribute to an unreliable rating, because there's no checking of the IP packet on its way. We don't know of any missed or lost during transmission. All of these things happen at the TCP layer. So IP can travel over many different types of media. This is what we mean by media independent. So we go over Ethernet, serial lines, optical fibers, wireless, satellites, whatever medium is being used to get the information from one point to another, the Ethernet frame doesn't actually change. That's what the data link layer is for, is actually controlling how it interfaces with the media. So the header, it's a fairly busy little diagram, this one, but the main ones you need to know about are the version, which says version 4, and then we have the service type, so this is priority, so your quality of service. Your time to live field is a way of making sure that the packet only travels for a certain amount of time on the network. If the time to live expires, then the packet is dropped. So that way, if the packet is caught in a routing loop, that eventually the traffic will be dropped off and it won't continue to escalate. The protocol is used to identify the protocol that it needs to talk to in the transport layer. Then we have the source and destination IP address. So the diagram is 32 bits in width, and basically this entire header is 20 bytes in size. So IPv4 was developed a long time ago, and it ran out of addressing space availability a long time ago. Only 4 billion addresses exist within IPv4, and they were not allocated in the most efficient way. So we had a couple of patches, if you like, that came out to extend the life of IPv4, and these were network address translation and port address translations and the CIDR notation. So we went from having a fixed network and host portion throughout the entire network to having a variable length, so that portionality could change, which was part of the CIDR patch. And then we started doing network address translation on that, like we would have at home. We have one live IP address that is shown to the world, and we can have many devices sitting behind that address when using the translation service. So IPv6 started out in the early 90s. I've seen a few tweaks to the way this is presented over the years. But the basic crux of the story is we've gone from a 32-bit address scheme to 128-bit. So that's increased the number of available addresses substantially. Currently, we only use 64 bits for network addresses, and the last 64 bits are for the individual devices on each network. Now, how we represent that does change a little bit, but that's the rough general rule of thumb. We don't have as many sections of the header, so the header fields handling is more efficient because there's less fields for it to process, and we don't need network address translation anymore because we've got so many addresses available. So looking at the IPv4 header on the left, we can see it has quite a lot of more fields in it than the one on the right. So basically, The main ones are still there, the purple ones, the version, and the source and destination IP address is the main ones that everybody talks about. We now call traffic class our type of service or our quality of service information, which works in conjunction with the flow label. Because we can actually do some funky stuff which is not covered at this level, we need to specify the payload length, and some of those funky things is we can stack headers within headers. So this is the field that says where the next header starts, and the hop limit is our time to live field. So the number of devices, intermediate devices that it can go through before it expires. So simplified header means it's more efficient in processing. It allows for auto configuration of addresses. This is where I said the first 64 bits is the network portion and the last 64 is the host. We can make that auto assign the host portion, and that speeds up the process considerably. And it gets rid of network address translation between private and public addresses. So I've basically gone through that earlier, so I won't go through this again. Basically talked about those fields. So okay, so how does a host decide to forward information? Well, it has three types of addressing. Itself, which has a loopback address of 127.0.0.1, or a local host address where the host destination is on the same network segment as itself, and remote host where it has to go through a routing device such that, okay, so a layer 3 device to be forwarded onto another network. So how does it find that device that does that forwarding decision for it? It has a default gateway. If you remember, when we set up a host machine, we give it a IP address, subnet mask, and a default gateway as a minimum set of information. Now that can be configured manually or via DHCP. And basically, if the destination address is not within the host local routing table, it will forward it to the default gateway. The default gateway will then determine what to do with the packet. It will look at the destination IP address and determine whether it has a path for it to be forwarded along. So let's have a look at the host routing table. We can use route print or netstat.-r. So our default gateway is our 0000 network. So this is the gateway address. So if we look at the little topology diagram here, we've got PC1, which is on the .10 of the 192.168.10 network, and the default gateway is .1, and it has a cost or a metric of 25 to get there. So basically, routing decisions use a cost value, which is called a metric, to determine how effective it is to get to a destination using the same protocol. So to get to the gateway, it's very cost effective, it's 25, whereas its loopback addresses cost 300, 106. Okay, so if you had to send information to the 192.168 address at a cost of 281, 224 network, which is via the loopback, costs 306. So when it looks up and if it sees, when it creates the routing table and if it's got multiple network destinations for the same network, it'll use the metric to determine the best one, which is the one it will insert into the routing table. Then it will become clearer as we do more routing activities in the labs. So the forwarding decision uses the costing. The way the costing works is basically a directly connected network has the lowest cost or is the most trusted type of information. Remote routes are routes learnt from other devices forwarding their routing table to it. So these are learnt routes going via another device. And then lastly, we have a default route where if it doesn't have any matching routes within its routing table, it will potentially send it out the default route. There's more rules around whether that will work or not, but that we'll cover that in another chapter. Routing table on a router is seen via the show IP route command, which you need to be in the privilege mode to issue, designated by the hash. If you remember from our earlier chapters, we have the different levels of privilege on a device: user, privileged, and global config. Excuse me. And so with this, we will see the routing table now. The L is for our directly connected local link. Okay, so this one is the other end of the cable. A C is our directly connected network. So if you have a look there, we are connected to the 192.168.10.0 network via the gigabit 0/0 interface. So we're talking about this interface here. And it's saying this IP address, specific IP address, the .1/32, is directly on that interface. So this is the local link address, and this is the network that is available via that local link. The Ds are our remote networks learnt via another device. So if you look here, we have the 10.110/24 network, which is connected via this address, which is router 2's closest interface, and it tells it what interface it needs to send it out on to get there. So, as I said in the last slide, I basically went through all this. So C identifies your directly connected network. L identifies the local link, which is the directly connected interface, its IP address there. So the D in this instance was for EIGRP, which is a type of routing protocol, and the breakup is the 90 is the administrative distance, which is how trustworthy the routing protocol is compared to other protocols. Then you have a metric, or the cost to get to that destination, and then you go via an IP address. So this is the next hop address, which is the address of the next device in the chain to get to that destination. Round trip timestamp, so basically how long it's been since it's learned an update from that device, and the outgoing interface to be able to get to that device. So if a packet arrives for the 10.1.1.0 network, it will look up the routing table, find an entry telling it to forward the packet out of serial 000, and I'll send it to this interface on router 2. So the next hop address is the closest interface address of the next device that will forward the IP packet onto its destination. Okay, now if this can be configured manually in a static route as well, but if you put in an IP address on a directly connected, or a manually configured route, it will then do an IP lookup on that network to find the interface. So if you're putting in manual entry into a router, it's advisable that you just specify the interface you need to send it out rather than the next hop, just to make it more efficient. So the next hop address then gets a lookup done on it along its connected networks, and you'll find a 209.165.200.224 network, which goes out of the serial 000. Okay, that's what I meant by the lookup. Routers are just a computer. Before we had routers, we just had another PC doing the job. We would just have many network cards in that device to act as a gateway. So as per any device, it needs an operating system, memory, network cards. Okay, so, and depending on the amount of traffic that goes through it, we need more CPU, more memory, more hard drive space, because the more complex operating systems that we need to install. So we will be looking at branch routers within this course, which is basically local area networks. So a router has a CPU and an operating system, and just like any device, it will have a heat sink. Now, routers are using passive, so they only have a heat sink, they don't have a fan. We will have fans in the case to do general air circulation through the case, but we won't have a dedicated CPU fan. So the memory of the router is broken up into basically the RAM, which has the running operating system in it, has our routing tables, our ARP tables, which is the table that matches layer 2 addresses to IP addresses, our running config file, and our buffers, so that this is temporary storage for a packet before it's sent or processed from an interface. We have NVRAM, where our startup configuration file is saved. This is the file that the device loads when it powers on. We have flash, which is the equivalent to our hard drives on these devices. We use a flash card, which we have our operating system stored on. And then within the ROM chips, we have the firmware, which has a power on self-test and to check all the hardware is stable before loading up the firmware, which basically is the initial startup process for the hardware, and it tells it to load the operating system as part of that startup process. So looking inside the case of a router, you'll have, just like a PC, you'll have power supply, some fans, and underneath these heat shields you'll find the interface cards, you'll have memory, you'll have the chipsets. So basically everything that you would find in a PC. So this is your motherboard. Okay, within that you will have your RAM card, which is generally slotted in from the outside for your flash card. Your RAM mounts just like it does in a PC. You'll have a slot that it connects into. You'll have a CPU, heatsinks, so on. The outside varies depending on the model, but basically the main things we need to concentrate on are our Ethernet ports. We will then have an auxiliary port, which isn't generally used that much anymore. It's an RJ45 socket, which we used to connect modems to, so that we would have a direct dial-in to configure the device if something went wrong remotely. Below that is, generally speaking, our console port, which is again an RJ45 connector, which is that blue ribbon type cable we talked about in class last term. Or in the newer devices, we can also use a USB type B interface for connecting directly to the device for console porting. Again, remember the console port is generally used for that initial setup config that we need to program. Okay, so our Ethernet ports or gigabit ports, we will have a compact flash slots, and then along here we'll have our enhanced high-speed WAN interface ports, basically expansion slots. So each one of these can take a card that has different functions. So we'll have a serial interfaces, we can have a card that basically does switching functions, so multiple Ethernet ports. We can do lots of things in these expansion slots. So basically we have our LAN ports in these expansion slots, our LAN ports in the gigabit ports, and then in the console ports we will have the console connection. So via our Ethernet or our serial ports, we would use Secure Shell or Telnet. Telnet's not the preferred method of configuration because it's unencrypted. So it's recommended that you use secure shell as is an encrypted form of communication when you're doing configuration changes. So the boot set basically tells it how to start up during the boot process. So we need to load the operating system. Once that's up in RAM and running, we can then load the startup config out of NVRAM into RAM, and note change of name. So we go from startup config to running config once it's in RAM. The router boot up process will start with post, which is a power on self-test of the electronics of the device. It will then go in the bootstrap, which is how to load the operating system, and you can locate and load the operating system from flash or a TFTP server. It will then load that into RAM. Next will be locate and load the startup config. So it will first look for startup config in the NVRAM. If it's not there, it will look for it on the TFTP server. Lastly, if those first two options do not meet a result, it will go to the console expecting a configuration to be entered manually. So show version command gives us a little bit of information that we may need about a device that we've not seen before. So it basically tells us what platform it is, C1900, that's the platform, and tells us what the operating system is, so Universal K9-M, and it's version 15, major release 2. Okay. So it'll tell you here how long it's been running, the uptime counter, and which file it loaded and from where. So this is saying it loaded the operating system off of flash, and that's the name of the operating system file. Then we have total bytes used and amount left over for free memory, if you like. Then it'll go through listing its interfaces that are on the device. So little expansion on our basic configuration steps, just a rehash from last term. So host name, so we go in user mode, enable, configure terminal to go in the global config, put in our host name, our enable secret password, then go put our passwords on our line console and our virtual terminal interfaces, then turn on service password encryption so that all these plain text passwords are given some minor protection. Enter our message of the day and then configure our interfaces and turn them on with the no shutdown command. The router, as per the switch, alright, there's no difference there. So basically the modes and everything between a switch and a router are basically the same. So on the router we will be doing the interfaces, IP address, subnet mask. You can put a description basically describing what it's connecting to. Turn the interface on with the no shutdown command, and then rinse and repeat for all the interfaces on the device. Now, to verify that basic operating interfaces, show IP interface brief will give you a brief summary of all the IP-based interfaces on the device. So it will give you the interface name, the IP address that's been configured with it, its status, whether it's running or basically. So here it was configured manually, the status is up and the protocol is up. So it's turned on and running. So the protocol is communicating with the protocol on the other end of the device. Okay, so that was then followed up with a ping command to test connectivity. So pinging a local host, it will go via the switch. It doesn't need to go up to the default gateway or nothing like that, because it's on the same network. So 10 can communicate with 11 directly via the switch. The router or default gateway does not need to get involved at all. The host is using its internal routing table to work that out. So how do we set a default gateway on these intermediate devices, just like we would on a PC? So for a switch, it's not a layer 3 device normally, so we have to configure it with a layer 3 interface, which is the virtual network interface running on the device. We give it an IP address, a subnet mask, just like we do on any other interface. But the next thing we might want to consider is configuring its default gateway. In other words, if we're talking to this switch for remote configuration, it needs to know how to get off this network and back via the gateway to get to that remote connection. So we use this with the IP default gateway command, which is configured via the global configuration prompt. Okay, so S1 bracket config close bracket hash is the prompt. And that's it. Oh, we had a few latecomers. Look at that.